Hello and welcome to today's video. In this video, we're going to talk about coordinate systems. Now that is a topic that is not directly related to linear functions, at least not on the surface, but it's an important building block of what we are going to do next. And to actually do that next step, we will need to define what a coordinate system is beforehand. So that section is titled Coordinate Systems. Now, the idea of a coordinate system is actually pretty simple. If you have a vector space and a basis for that vector space, then any vector in the space can be written as a linear combination of the basis vectors. So for any vector in a space, you can write something like V is a linear combination of V1, V2, and so on up to the dimension, let's say Vn, like this. In other words, if you want to store that vector V, for example, using a computer or something like that, then what you would do is you would store those coefficients here, the lambda 1, lambda 2, and so on. And of course, you'd need to remember the basis. If you were using a different basis, so if you'd replace the v1 to vn by different vectors, then of course the coefficients would also change. So that representation of a vector by its coefficients depends on the choice of basis. A popular choice of basis is to use the unit vectors, u1 to un. And that's what we usually do. But of course, from a mathematical point of view, that is completely arbitrary. It may look simple, but there may be good reasons to choose a different basis. For example, say you are in a system where it's much easier to move in one direction than in another direction, then you might want to scale those directions differently to express that. That would mean that on one axis, the spaces between two units are longer, and on another axis they might be shorter, like this here. Or you might want to have directions that are not perpendicular to each other. You might want to have a coordinate system that looks like this. For example, if that is for some reason a preferred direction of motion, let's say the wind blows in that direction, and you want to have that direction as one possible direction of motion, but you don't want to change the others, then this might be a valid choice of coordinates. And basically what a coordinate system is in a vector space is just a basis, and of course you also have to impose an order on that basis so that you know the first coordinate of a vector stands for the coefficient of that basis vector, the second stands for a coefficient of that basis vector, and so on. And that is what we are going to do in our definition now. So here's the formal definition of a coordinate system in a vector space. Let V be a finite dimensional vector space and let's say the dimension of V, we'll abbreviate that as n. Then, first part of our definition, a coordinate system on V is an n-tuple. So a tuple of the form B1, B2, and so on up to Bn, such that the set B1, B2, and so on up to Bn is a basis of V. So basically what we have here is an ordered basis. And often we just write down the basis as a set and assume the order coming from the indices. Part 2, we're going to introduce a little notation to make the following a little easier to comprehend. So if we have such a system, let B be equal to B1, B2, and so on, up to Bn, let that be a coordinate system for V. And let V be a vector in capital V. Then, of course, that vector is first not depending on any coordinates. We have an abstract vector in that space, an element in that space. Now we can assign coordinates with respect to this given coordinate system. And these coordinates, that will be called the coordinate vector of V. So the coordinate vector of V with respect to the coordinate system B is the vector, and we'll denote that as V braces B, like this. That's a vector consisting of lambdas, n coefficients like this, where lambda 1 to lambda n in R are the uniquely defined coefficients with the property that V is a linear combination of those with respect to the basis vectors collected in B. So that's lambda 1 B1 plus lambda 2 B2 and so on up to lambda n Bn. And of course this vector here, this coordinate vector, that is always an element in R to the n, where again n is the dimension of V. So even if V is an abstract vector space, something like polynomials of a certain degree, then it still has coordinates in R to the n once you fix a basis, once you fix a coordinate system. So here's a couple of examples to illustrate that point. Let's first start with an ordinary vector space. We'll do R to the 3 as our first example. And we'll fix a basis in R to the 3. We'll use the basis 1, 0, 0, 1, 1, 0, and 1, 1, 1. So that's not the usual canonical standard coordinate system. That would be the unit vectors, but a different coordinate system. And let's take a vector. We'll take the vector V. Let's say 1, 2, 3. Right? That is a vector in capital V. And we want the coordinates of that vector. So the question is, compute the coordinates of V with respect to the basis B. Now what we have to do is, we have to represent V in terms of the basis. So we have the basis vectors 1, 0, 0, 1, 1, 0, and also 1, 1, 1. And now we're looking for lambdas, for coefficients that we can multiply these vectors with. such that the result of this linear combination is actually V. Now, if you're doing this, let's first have a look at the last line here. You can see that there's zeros in the orange and the green vector, so only the blue one has an entry here. So this 3 entry here, that can only be obtained from that vector here. So we need that one 3 times. So that's the first coefficient that we get. Then, if we're looking at the second line, we can see that there's a 0 in the orange vector. The 3 in the blue vector is already fixed, so we need to use the green vector to repair that. Up to this point, we have 3 times 1, that's 3. We need a 2, so we need to subtract 1 here in the green part. So there's a -1 coefficient here, that's necessary. We get the 2. And finally, for the first line, the green and the blue part have already been fixed. So to get the right coefficient for the orange vector, we need to look at that. We have a -1 here and a +3. So currently the entry would be -1 + 3, that's 2. We want it to be 1. So we need another -1 here in front of the orange vector to subtract 1 from that. Okay, so what we get is the coordinate vector of V with respect to B is then -1, -1, and 3. And again, that depends on the choice of bases. Let's choose a different basis. So if we choose, let's say, B prime to be -1, 1, 0, 1, 0, 1, and 0, 0, 2. Then for the same vector, we get a different representation. Again, what we have to do is we have to find the right coefficients here. So we have -1, 1, 0, 0, 1, 1, 0, 1, and 0, 0, 2. And we have to find coefficients here, here, and here, such that we obtain this vector as a result. Now, for the right coefficients, of course, what we could do is we could just solve a system of linear equations to get those coefficients. And in general, that's what we would do. In this case, however, it's easy to see the right solution, so we don't bother with a formal solution of a system of linear equations. Looking at line 2, you can again see there's 2 zeros, there's 1 entry, so this here will be responsible for the 2. And that means we need a 2 here in front of that vector. Now, looking at line 1, there's again a 0 entry here in the last one. Yeah, that is already fixed at -2, so we can still play with this entry here. We want a 1. So if we have a -2 here and we want a 1, then of course we need to add 3. So we get +3 right here. And finally, let's take a look at the last row. So we have 2 times 0, we have 3 times 1, that's 3, and something times 2, and we need that to be 3. Well, of course, we can just take a 0 here to get what we want. So that's the solution. And remember, the solution is unique because B prime is a basis. And now with that, the coordinate vector of V with respect to B prime, that would be a 0 as the last coordinate, a 3 as the middle coordinate, and a 2 as the first coordinate. So that is the coordinate vector of V, the same vector V, with respect to a different basis. And you can see how these coordinates, of course, change with the choice of basis. Let's have a look at a different example, part B. So in this case, we are going to take a vector space that is a subspace of R3. So this time we're going to take the vectors 1, 2, 1 and -1, 0, 1, and we're going to define V as the span of these two vectors. So anything that's generated by these two vectors, that's a subspace of R to the 3. And geometrically what we have here is a plane in R to the 3. Now let's take a vector here, V, let's say this is 2, 6, 4. And I'll just let you know that is actually contained in capital V. You might not see that immediately, and you don't have to. And again, we choose a basis, and of course the easiest basis that we could choose is just to use these two vectors here. Right? So let's choose this basis. The order, of course, is arbitrary. And then we want the coordinates of that vector of V with respect to P. What is that? Well, again, we need to represent V as a linear combination of the basis vectors. So we need to represent that as a linear combination of 1, 2, 1 and -1, 0, 1. And to that, again, we could solve a system of linear equations. We don't have to in this case, or we do have to, but it's easy. Looking at that second line, we can see that this 6 here can only be created using this 2. The second vector will not contribute anything. So we need 3 times the first vector. That's fixed already. And if we have that, then let's have a look at the 2 here, for example. We have 3 here and the -1 here. So the right coefficient to create the 2 would then be a 1 in that place here. And of course, we have to check whether that also works for the third row. So here we have 3 plus 1, that's 4. And indeed, 4 is correct. So that confirms that V is indeed a linear combination of those two vectors. That confirms that V is indeed contained in capital V. So the coordinates of V with respect to B are then 3 and 1. And now you'll see that this coordinate vector is indeed contained in R2. And that's because the dimension of V is 2. Even though V is embedded in a higher dimensional space, in R to the 3, this V can be described by just 2 coordinates. So the idea is basically you have a plane in R3 somewhere, and then there's a coordinate system that lies in that plane. And of course, within the plane, you only need one axis like this, one axis like this. You have 2 coordinate axes in that plane. And that gives you a valid coordinate system for all vectors that lie in the plane. Okay, so for V, 2 axes, 2 coordinates are sufficient, and that means a coordinate vector for a vector in that space V might look like this. Just has 2 coordinates. Finally, let's have a look at an abstract example as well. It might even be easier to understand in that case. Let's say we take the space P2 of polynomials of degree at most 2. And of course, we can also use a basis for that space here. One possible basis would be to take the functions 1, x, and x squared. Of course, you can compose any polynomial of degree at most 2 of these 3 building blocks here. So in particular, the dimension of P2 is 3. And we take a vector in P2, and let's say we take the vector 1 minus x squared. It's a very simple one. And again, we would like to have the coordinate vector of V with respect to B. What we'd have to do is simply represent that V here as a linear combination of our vectors 1, x, and x squared. And to do that, well, we'd have to use 1 once. There's no x in there, so that would be 0 times x. And the x squared, there's a minus 1 in front of that, so here's minus 1x squared. And that means this coordinate vector here, with respect to the basis b, that would be 1, 0, and minus 1. And again, we could choose a different basis. Let's do that. So for example, if we choose b prime to be 1, 1 plus x, and 1 plus x squared, we can again ask for the representation of v as a coordinate vector with respect to b prime now. And again, what we have to do is we represent v, 1 minus x squared, as a linear combination of those basis vectors here. And now the basis vectors are 1, 1 plus x, and 1 plus x squared. And the question is again for the right coefficients. Now we look at the x squared first. There's a minus x squared here. The only x squared in our bases appears here. So we need to take that times minus 1 to get the x squared part, right? Then we have minus 1 minus x squared, and we need to make up for that minus 1. We want a plus 1. And of course we can use this first part here. We just need that 2 times. So it's 2 minus 1 minus x squared, and that's exactly 1 minus x squared. So we don't need the green part. So that gets a coefficient of 0. And that means we, with respect to b prime, the coordinate with respect to b prime, that is 2, 0, and minus 1. So again, different basis, different coordinate system means a different coordinate vector. The vector in the background, the polynomial, v, that did not change. It's just the representation that changed because we're using a different coordinate system now. Yeah. So in geometric vector spaces like r to the 3, r to the 2, the point in space stays exactly at the same place. We're just changing its description. We're changing the axis. We're not changing the point. And changing the axis means changing the coordinates. So that's what we do with the coordinate systems. And in the following videos, we're going to apply this idea to linear functions, linear mappings, to obtain a concise representation of those linear mappings. And I hope I'll see you in one of these videos.